Next, you will be hearing a presentation from Wei-Che Chien. Professor Chien is currently an assistant professor with the Department of Computer Science and Information Engineering, National Donghua University, Taiwan. His research interests include wireless, rechargeable sensor networks, 5G mobile networks, IoT, fog computing, and cloud computing. Today, he's going to give us a presentation entitled Deep Learning Networks for Cellular Traffic Prediction in the IoT. Ladies and gentlemen, let's welcome Professor Chien.
Hello everyone, my name is Wei-Che Chien. I'm an assistant professor. I'm coming from National Donghua University, Department of Computer Science and Information Engineering. It's my great pleasure here today to share my research results. Before I talking about technology, I would like to express my sincere thanks to the people, especially Professor Hualien, who invited me to share my research results. Okay, the title of today's presentation is Lightweight Deep Learning Networks for Cellular Traffic Prediction in IoT. As you guys didn't know who I am, let me introduce myself. I just graduated from National Chien University in Taiwan in 2020, so I just graduated for a year. I'm a brand new professor now. I'm also a Deputy Secretary General in Institute of Information and Computer Machinery in Taiwan. Therefore, if you are a master student or a PhD student, you may consider to submit your thesis or your dissertation to our society. We have best thesis award and the best dissertation award every year. I'm also associated editor for HCI's ZIT, IEEE Networks, and JLC. Welcome to submit your paper to the journal. Okay, I would like to divide my talk into 6 sessions. First of all, I would like to introduce why do traffic prediction problems need to use the lightweight deep learning model and what are benefits. In session 2, I would like to introduce the current study of cellular traffic prediction, which are based on deep learning. Then I will come to propose a lightweight model called Lightweight Spatial Temporal Convolution Neural Network Model. In next session, I will present result analysis. Finally, I will conclude my talk with several highlights. Let's talk about what the traffic prediction problem is and why we need to use a lightweight deep learning model. The left figure shows the evolution of mobile data consumption, and the right figure shows mobile backhaul traffic growth bandwidth. We can see that the rapid development of multimedia, smart city, IoV, and other IoT applications have led to an exponential increase in data traffic year by year. According to this trend, the cellular network will become more and more congested, and the quality of service of users may decrease. According to the traffic prediction result, we can know which area have more traffic demand and adopt some strategies such as adding base stations or allocating network resource Therefore, let's talk about traffic prediction method, which can be divided into two types, including physical methods and statistical methods. First type mainly utilize the laws of physics and user behavior to achieve predictions. The second type focuses on exploiting the relationship among historical data, which are adapted to establish the prediction model. In general, the physical method has advantages in long-term prediction. In contrast, the statistical method is better in short-term prediction. Moreover, there are many applications based on cellular traffic prediction. Most of them have strict requirements, such as industrial Internet of Things. Accurate traffic prediction in short-term prediction is needed to avoid unexpected situations, so it is suitable to use the statistical method. The statistical relationship in the historical data could be modeled by various methods. It can be classified as linear models, such as autographic models, moving average models, and autographic integrated moving average model, and nonlinear models, such as artificial neural networks, recurrent neural networks, long short-term memory, and get recurrent unit. However, large scale and high accuracy cellular traffic prediction is extremely challenging. The reasons are as follows. For temporal dependencies, cellular traffic will change over time due to user behavior, network applications, and diverse network requirements. For spatial dependence, data traffic includes mobile users and static users. Mobile users introduce spatial dependence into the cellular traffic among base stations. In other words, when a user is moving and using a service at the same time, the spatial dependence of cellular traffic will affect the prediction results. For spatial temporal dependencies, there are many factors, including population, building holidays, and various social activities. These influential factors further complicate spatial temporal dependencies and influence cellular traffic. To exactly predict cellular traffic, deep learning is a promising technology. Although using ARIMA can find the solution that closest to optimal solution with lower complexity, the performance of STM over ARIMA in general, especially when the training data is sufficient. However, ARM-based method cannot process the spatial temporal dependencies problems. Some researchers use hybrid method to solve this problem. The prediction performance is well, but these methods are complex and contain many parameters. In other words, these deep learning methods often require many computational costs, memory, and energy to train a model. For a cellular traffic prediction problem, real-time prediction is required. If each base station is equipped with high-speed computational capacity equipment, it is a lot of cost for the operator. Therefore, a lightweight deep learning model is a suitable solution. Deep learning models can be compressed by methods such as pruning, quantization, joint training, and distillation. However, different deep learning model comparison methods are suitable for different problems. In this research, we are meant to develop a lightweight deep learning model for a cellular traffic prediction problem. There are three main contributions of this research. We consider spatial temporal dependencies among base stations and propose a lightweight deep learning model for cellular traffic prediction problem. We optimize the hyperparameters of the proposed lightweight deep learning model. The second contribution is that the proposed architecture and the model can reduce the operator's equipment cost and save the calculating cost. And then let's talk about the current study of cellular traffic prediction. The temporal dependence of traffic has been discussed in many studies. Most of exciting methods to solve this problem are based on architecture of recurrent neural networks. However, the recurrent neural network architecture is difficult to achieve parallel computing and is with a bunch of parameters. Although recurrent neural network architecture can effectively capture temporal features, it cannot solve the problem of spatial dependencies of cellular traffic data. Therefore, researchers will propose different models to solve the spatial temporal dependence problems, which can be simply divided into single models and hybrid models. In single models, DenseNet was proposed to predict cellular traffic. DenseNet is a densely connected CNN, which models the traffic of different base stations and capture spatial temporal dependencies of different base stations through convolution operations. However, DenseNet is very memory intensive. In hybrid models, the architecture of autoencoder connected to LSTM has been proposed. LSTM is adapted to extract temporal features, and autoencoder is used to extract the spatial features between different base stations. However, the encoder will compress extract features, which may destroy the spatial temporal features of neighboring base stations. Next, I will introduce the problem definition for traffic prediction. For a cellular traffic prediction problem, our first goal is to propose a lightweight architecture that can consider the spatial temporal dependencies of traffic data. The second goal is to achieve high accuracy predictions. The third goal is to minimize the hyperparameters. In order to achieve the three goals just mentioned, we propose lightweight spatial temporal convolutional neural network model for cellular traffic prediction. And let's talk about this method. This is the flow chart for the research. First, preprocess the network traffic data, then use the STCNN model we proposed for training, and finally analyze prediction result. Next, let's talk about our traffic data. We use this data set as test data, which is from the European telephone service provider Telecom Italia. The dataset was collected in Milan from November 10, 2013 to January 1st, 2014. This dataset is temporarily aggregated every 10 minutes. There are a total of 10,000 base stations in this dataset. We take 900 of them as input data and split the data into 90% training data and 10% testing data. There are 11 hyperparameter settings are adjusted to improve prediction accuracy. In order to consider the spatial temporal dependence of traffic data at the same time, we design a lightweight neural network model based on CNN, but CNN can only capture the data features of the region. Therefore, in the data preprocessing part, we have performed some conversions so that LSTCN can capture the features of spatial temporal dependence of traffic data at the same time when performing convolution operations. On the right figure is a segmentic diagram of network traffic. Each grid represents a base station, and the value of the z-axis represents the network traffic at the time interval t. We convert the original two-dimension array into a one-dimension array by equation 4. Next, we merge the converted one-dimension arrays. For example, the traffic data of time unit 1 to 3 is first converted from two-dimension to one-dimension array. Then merge the network traffic data of these 3 units of time into a two-dimension array. Okay. This is the process of our data preprocessing. Through such data conversion, when performing convolution operations, the temporal dependence features can be extracted from vertical axis, and the spatial dependence features can be extracted from the horizontal axis. We evaluate the performance of cellular traffic prediction based on 3 metrics, including mean absolute error, root mean square error, and mean absolute percentage error. Next, let's talk about the proposed lightweight neural network model. There are many cellular traffic prediction methods that have been proposed. High accuracy prediction results are usually accompanied by high computing capacity requirements. In order to reduce the cost of high specific equipment, we evaluate and analyze the lightweight mechanism of mobile net V3 and design and appreciate the lightweight neural network model for the network traffic data after data preprocessing. Since the lightweight methods are easy to destroy the structure of the raw data, not all mechanisms are applicable. This table shows the lightweight mechanism used in this study. Width multiplier and the resolution multiplier can reduce computational cost and the number of parameters through controlling the input width of a layer and the input image resolution. But it will destroy spatial temporal features. Therefore, we didn't adopt these two lightweight methods. Pooling layer is usually used after convolution layers. Average pooling and maximum pooling are commonly used methods. Generally, the error of feature extraction mainly comes from two types. First is that the variance of the estimated value increases due to the limited size of neighborhood. The second is that the error of estimated average value is caused by the deviation of parameters in the convolution layer. Average pooling can reduce the first type of error and more retain the background information of image. And maximum pooling can reduce the second type of error and more retain the textual information. However, this method will destroy spatial temporal features. Therefore, we didn't adopt these lightweight mechanisms. The advantage of batch normalization is that after normalizing the features of each layer, we can ensure that the static of output of each layer is fixed. It can avoid the mutual influence of different layers when adjusting parameters. Batch normalization can speed up training and prevent the problem of gradient vanishing. However, batch normalization depends on the batch size. It is unsuitable in this problem. According to our input data format, we adopt the following mechanism to implement a lightweight model, including linear bottleneck, depth-wise separable convolution, point-wise convolution, inverted residual sequence and excitation, and edge switch. The linear bottleneck consists of point-wise convolution and depth-wise separable convolution. It can replace traditional convolution layer to reduce parameters and calculations. The traditional convolution is that each kernel map needs to do convolution with all channels. Linear bottleneck separates it. Point-wise convolution only does 1 times 1 convolution for all channels, which is used to run features between channels. The depth-wise separable convolution uses different convolution kernels for each input channel. In other words, it only maps the spatial temporal of traffic data and not cross-channel correlations. Moreover, the architecture of the inverted residual is the opposite of traditional residual structure. First, the input feature map is enlarged by 1 times 1 convolution. Then, 3 times 3 depthwise separable convolution is used to perform convolution operation. And then finally, the 1 times 1 convolution is used to reduce its dimension. The advantages of inverted residual are multiplexing features and mitigating feature degradation. For a cellular traffic prediction problem, traffic data of each base station has spatial temporal dependence. So we propose a spatial temporal input data format based on convolution neural network architecture. In order to avoid feature data being destroyed due to compression, this research proposes a lightweight convolution neural network model, including 2 traditional convolution layers, 5 linear bottleneck layer, and inverted residual layer. First, we use a convolutional layer to get spatial temporal features. Generally, if the tensor dimension is lower, the multiplication calculation of convolutional layer is smaller. The overall calculating speed will be very fast when the entire neural network is a low-dimensional tensor. However, if the filters of convolutional layer use low-dimensional tensors to urban features, it is hard to extract enough overall information. Therefore, we may prefer a high-dimensional tensor to urban features. The computational complexity and the high-dimensional tensor become a trade-off problem for lightweight model design. In order to capture the feature more deeply, a 5-layer bottleneck with expansion factor architecture is used to connect the convolution layer. This is the lightweight model proposed in this research. In each bottleneck layer, point-wise convolution, depth-wise convolution, and point-wise convolution are included in the sequence. The first layer of point-wise convolution is also called expansion layer. It is used to expand the dimension. The third layer of point-wise convolution is also called the projection layer. It is used to compress data and make the neural network smaller. Since both the expansion layer and the projection layer have parameters for learning, the entire neural network structure can learn how to better expand data and recompress data. Finally, convolution layer and the fully connection layer are connected. Next, we further expand the mechanism in each bottleneck layer. Each bottleneck layer has has three lightweight mechanisms, including depth-wise separable convolution, screens and excitation, and inverted residuals. The depth separable convolution is composed of two point-wise convolution and depth convolution. And let's talk about the performance evaluation for cellular traffic prediction. We evaluate the proposed lightweight model with Google Collaborate, the simulation tool Adobe class. The details are shown in this figure. These two figures show the traffic prediction results of two types of base stations. The first type of base station has a large traffic range, but the traffic is distributed evenly. The second type of base station has a small traffic range, but the traffic varies greatly. We adjust the hyperparameters to observe the prediction results of these two types of different base stations to optimize the proposed lightweight model. This slide shows the experimental results. The blue line is original data, the green line is training data, and the red line is testing data. And we can see that for base stations with stable traffic changes, the prediction effect is very good. But for the base station with drastic changes in traffic, the prediction result can be improved. The figure shows a comparison of batch size from 2 to 412. A large batch size can reduce training time and improve stability, but it will result in a decrease in the generalization ability of the model. In our experiment, the batch size is set to 32 to achieve the most accurate prediction. The figure shows the comparison of the optimizers, including RMS Probe, ADA Grade, ADA Max, and ADAM. ADAM combines momentum and ADA Grade. Therefore, ADAM returns the characteristic of momentum that the learning rate will be first in the same direction dimension, and the learning rate will be slower when the dimension changes. In addition, ADAM also adjusts the learning rate of the square value of the path gradient. Each learning rate will have a certain range, which will make the parameter update more stable. Therefore, we choose ADAM as the optimizer. The figure shows the comparison of the time step. The time step affects the extraction of temporal features. The large time step will cover the traffic information for multiple intervals. Relatively, it will increase the size of input data and the training time. In this study, it has the best prediction performance when time step is set to 3. The right figure shows the comparison of number of filters from 16 to 96. The left figure shows the comparison of convolution kernel size from 3 times 3 to 9 times 9. For the traditional convolution layer, the number of filters and the kernel size is positively correlated with the features that can be captured. But more filters or large kernel don't mean higher accuracy of traffic prediction. On the contrary, it will increase the training time. The suitable number of filters and the kernel size in this research is 32 and 3 times 3. The figure shows the comparison of threads. Using thread can greatly reduce the extracted feature map, which can reduce the calculation of the model and adjust the size of each layer of the neural networks. However, a big thread may cause problem of insufficient features, resulting in reduced accuracy. In this research, 5 threads have the best accuracy. The table is the comparison of the bottleneck block types. We tested the 4 types of depth of bottleneck block, including shallow deep type and deep shallow type, shallow deep shallow type, and deep shallow deep type. Experimental results shows that the architecture of the type 3 has better performance. The table shows the comparison of different activation function types. 9 different types of activation function are designed according to the type of bottleneck block. We test the result of using residual for all convolution layers. It's type 1. Residual stacks for all convolution layers. It's type 2. H-switch for all convolution layers is type 3. And using them together from type 4 to type 9. Residual and residual 6 will destroy the features when input data is a negative number, resulting in lower prediction accuracy compared to H-switch. Therefore, we used 3 commonly used activation functions to test and compare results. Finally, the type 5 architecture is used in this research. We also compare the different SE types. We test the utility of SE in different linear bottleneck layer and found that the use of global average pooling by SE will cause the destruction of features and lead to poor prediction results. Therefore, this study didn't use SE. There are some hyperparameter settings. Please refer to the list table. In order to evaluate the proposed library model, we compare it with the current technologies, including ARIMA, getter recurrent unit, long-short memory, self-attention, convolutional neural network, and so on. We can find that our proposed method has better prediction results. This figure shows the prediction results of the second type of base station. We can see that the proposed model also have good performance. Finally, we compare the performance of proposed lightweight model with exciting technologies which are based on the convolution neural networks. Most of the methods for network traffic prediction use the architecture based on both recurrent neural network and convolution neural network to capture spatial temporal feature. But the architecture of residual neural network require a lot of parameters, which means that it is difficult to achieve real-time training. In order to predict the traffic of massive base stations at the same time, consider spatial temporal features, and design a lightweight model. We preprocess the input data as a spatial temporal sequence for cellular traffic prediction. By adjusting the hyperparameters and the architectures, the proposed lightweight model can not only avoid destruction of features, but also improve the accuracy of prediction and reduce the model size of the proposed lightweight method at the same time. In addition, compared with other related methods, the parameters, flops, and the training time are also significantly reduced. Furthermore, in order to optimize the prediction performance and reduce the parameters of neural networks, we also use a Meta-heuristic algorithm to adjust the hyperparameters. We use the simulated annealing algorithm to optimize the hyperparameters of the convolution kernel size, the number of convolution kernels, and the convolution strides. A flow chart of hyperparameter adjustment strategy is shown in the left figure, and the right figure is the proposed algorithm. The figures show the comparison of MSE and parameters. The red line is the greedy algorithm. The blue line is the simulated annealing algorithm. Greedy-based algorithm shows a relatively stable downward trend, while simulated annealing algorithm have the opportunity to accept poor solutions at an early stage to avoid quickly falling into local optima. The result shows that the simulated annealing-based algorithm can get better accuracy and fewer parameters. The table is the comparison of parameters and accuracy. The first method uses the empirical rule to adjust parameters. The second is to use the greedy-based algorithm. The third is to use the simulated annealing-based algorithm. The simulated annealing-based algorithm has higher accuracy and fewer parameters than empirical rules and greedy-based algorithm in terms of accuracy and parameter quantity. There are many hyperparameters that need to be adjusted by deep learning model, but the empirical rule is difficult to achieve good results. The simulated annealing-based algorithm method can search for better hyperparameters, but the search process requires additional training time. In this study, the simulated annealing-based algorithm needs to use more running time than greedy-based algorithm. Or better result can be obtained by using this method to adjust hyperparameters. It takes extra time to train the model for the first time. Finally, I will conclude my talk with several highlights. This research considers spatial temporal dependencies of cellular traffic to design a lightweight model called LSTCNN and optimize the hyperparameters of this model. Compared with the related spatial temporal neural network model, the proposed model can greatly reduce the parameters, flaws, and training time while maintaining a certain accuracy. And in order to reduce the computational resource for cellular traffic prediction while maintaining a certain degree of accuracy, this paper proposed a hyperparameter optimization strategy based on a simulated annealing algorithm for lightweight neural network. Although we can get the better performance, but the assay-based method also need to take extra time to train the model for the first time. This is conclude my talk. Thank you everyone for joining me with this session.